Hello there. Before you close your eyes tonight, before you drift into sleep, I want to share something with you. Something that changes everything we thought we knew about our place in the universe. Right now, as you're settling into comfort, as you're finding that perfect position, you're floating. We're all floating. Not just on this planet spinning through space, but inside something far more mysterious. Something vast beyond comprehension. We're trapped inside a void. A cosmic emptiness stretching 2 billion light years across. And we just proved it. Take a breath. Let that sink in for a moment. 2 billion light years of mostly nothing, and we're somewhere near the center of it. For decades, astronomers suspected something was off about our cosmic neighborhood. The numbers didn't add up. The universe seemed to be expanding at different rates depending on where we looked. Some called it the Hubble tension. Others thought our instruments were faulty. But in July of 2025, scientists at the University of Portsmouth published something extraordinary. Using echoes from the Big Bang itself, sound waves that have been traveling through space for over 13 billion years, they proved it. We live inside a giant hole in the universe, and the evidence is 100 times stronger than any alternative explanation. Now, you might be wondering what that means. What does it mean to be trapped in a void? Is it dangerous? Should we be concerned? And perhaps most importantly, how did we end up here? These are the questions we'll explore together tonight, but there's no rush. We have time. All the time you need to drift into sleep while we float through this cosmic mystery together. So get comfortable. Let your body relax. Let your mind wander through the vastness of space. Because what we're about to discover is both humbling and beautiful in ways you might never have imagined. Let's start with something simple, something you can picture. Imagine you're looking at the night sky. On a clear night, away from city lights, you might see a few thousand stars with your naked eye. Each one of those stars is a sun, much like our own. Some smaller, some incomprehensibly larger. Now imagine you could see farther. If your eyes could detect the faint light from distant galaxies, that dark space between stars would fill with countless points of light. Billions upon billions of galaxies, each containing hundreds of billions of stars. The universe, as we typically imagine it, is full, crowded even, a cosmic metropolis of matter and energy stretching in every direction forever. But that's not quite true. The universe isn't uniformly full. It's more like a sponge, or perhaps like sea foam frozen in time. There are regions where galaxies cluster together in spectacular walls and filaments, great cosmic highways of matter stretching hundreds of millions of light years across. And then there are the voids, the empty spaces, the gaps in the foam, where almost nothing exists. These aren't just small gaps, they're enormous. Some voids stretch for hundreds of millions of light years, with almost no galaxies inside them at all. Just darkness, emptiness, the cosmic equivalent of the deep ocean, where life is sparse and strange things happen in the dark. For a long time, astronomers thought we were lucky. We live in the Milky Way, a fairly large spiral galaxy in a relatively busy part of the universe. We're part of something called the Local Group, a small collection of galaxies, including Andromeda, and about 50 smaller galaxies, all bound together by gravity. And the Local Group sits on the outskirts of an even larger structure called the Virgo supercluster, a massive collection of galaxy groups and clusters spanning about 100 million light years. We thought we were in the thick of things, in the heart of the cosmic city. But something was wrong. The measurements weren't making sense. You see, astronomers have two main ways of measuring how fast the universe is expanding. The first method looks at nearby objects, relatively speaking. Exploding stars called supernovae in galaxies millions of light years away. By measuring how bright these explosions appear and how fast they're moving away from us, we can calculate the expansion rate of the universe. This rate is called the Hubble constant, named after Edwin Hubble, the astronomer who first discovered that the universe is expanding at all. The second method looks much farther back in time. It examines the cosmic microwave background, the afterglow of the Big Bang itself. This is light that has been traveling through space for over 13 billion years, since just a few 100,000 years after the universe began. By studying the patterns in this ancient light, astronomers can calculate what the expansion rate should be today, based on our models of how the universe evolved. Here's the problem. These two methods give different answers. And not just slightly different. The difference is significant enough that it can't be explained by measurement errors or statistical fluctuations. When we look at nearby supernovae, the universe seems to be expanding faster than it should be based on the cosmic microwave background, much faster. This discrepancy became known as the Hubble tension, and it's been keeping cosmologists awake at night for years. At first, scientists thought the equipment might be miscalibrated. Maybe our measurements of distant supernovae were off somehow. Or perhaps our models of the early universe needed tweaking. Dozens of papers were published proposing different solutions. Maybe dark energy, that mysterious force pushing the universe apart, was stronger than we thought. Maybe gravity works differently on cosmic scales. Maybe there's some unknown type of particle or field we haven't discovered yet. The theories multiplied, but none of them quite fit all the data. And then someone suggested something different, something almost uncomfortably simple. What if we're not in a typical part of the universe? What if our local measurements are skewed because we live somewhere special? Not special in a good way necessarily. Special in the sense of unusual. Atypical. What if we live in a void? The idea wasn't entirely new. Astronomers had known about cosmic voids for decades. They'd mapped several of them. But suggesting that we might live inside one was controversial. It felt almost like a return to pre-Copernican thinking. The idea that Earth occupies some special position in the cosmos. For 500 years, astronomy has been teaching us the opposite lesson. We're not at the center of the solar system. The solar system isn't at the center of the galaxy. Our galaxy isn't at the center of the universe. There is no center. We're ordinary, typical, unremarkable in every way. That's the Copernican principle, one of the foundational assumptions of modern cosmology. But what if, in this one specific way, we're not typical? What if the Copernican principle, while generally true, doesn't apply to our immediate cosmic neighborhood? This is where the evidence from sound waves comes in. And to understand that evidence, we need to talk about something called baryon acoustic oscillations. It's a mouthful of a term, I know. But the concept is actually quite beautiful once you understand it. Picture the universe about 380,000 years after the Big Bang. It's still very young, very hot, and very dense. The entire universe is filled with a thick fog of hydrogen plasma, so dense that light can't travel through it. Photons, particles of light, are constantly being absorbed and re-emitted by electrons. It's like trying to see through clouds so thick that you can't see your hand in front of your face. But this fog isn't calm. It's churning with sound waves, massive pressure waves, created by the uneven distribution of matter in the early universe. These sound waves are traveling through the plasma at about half the speed of light, pushing matter around, creating regions of higher and lower density. Then something remarkable happens. The universe expands enough and cools enough that electrons and protons combine to form neutral hydrogen atoms. Suddenly, the fog clears. Photons can travel freely through space for the first time. This moment is called recombination, and it's when the cosmic microwave background radiation was created. But here's the key part. When the fog cleared, those sound waves didn't disappear. They froze. The matter that had been pushed around by those pressure waves stayed where it was, creating a pattern. Regions where matter had been compressed by the sound waves now contained slightly more galaxies. Regions where matter had been rarefied contained slightly fewer. This pattern is still visible today, over 13 billion years later. When astronomers map the positions of millions of galaxies, they can see it. Galaxies aren't distributed completely randomly. There's a subtle tendency for galaxies to be separated by a specific distance, about 500 million light-years. This distance is the wavelength of those ancient sound waves, stretched by the expansion of the universe. It's like a cosmic ruler, a standard measuring stick imprinted on the structure of the universe itself. And this is where the Portsmouth team made their breakthrough. They used data from multiple galaxy surveys, observing millions of galaxies across vast volumes of space. By analyzing the distribution of these galaxies and looking for the baryon acoustic oscillation signal, they could measure the local expansion rate of the universe with unprecedented precision. And what they found was stunning. The local expansion rate, the Hubble constant measured from relatively nearby galaxies, really is different from the global expansion rate measured from the cosmic microwave background. The Hubble tension is real. It's not a measurement error. It's not a calibration issue. It's a genuine physical difference. But why? Why would the expansion rate be different in different places? The answer, according to their analysis, is that we live in an underdense region. A void. A region where there's less matter than average, which means gravity is weaker, which means the expansion proceeds faster. It's like being in a bubble within the cosmic foam. Inside the bubble, things expand faster because there's less gravity to slow them down. Outside the bubble, in the denser regions of the universe, expansion proceeds at the normal rate. How big is this void? That's the truly staggering part. The Portsmouth team calculated that to explain the Hubble tension, we'd need to be living in a void about 2 billion light-years across. That's enormous, even by cosmic standards. It's about 1% of the diameter of the observable universe. It would encompass not just our local group of galaxies, not just the Virgo supercluster, but an entire complex of superclusters, tens of thousands of galaxies, all floating in a region of space that's less dense than the cosmic average. And the evidence for this is strong. When the researchers compared this void hypothesis to alternative explanations, they found it was 100 times more likely. 100 times. That's not a marginal preference. That's overwhelming evidence in scientific terms. It doesn't mean we're absolutely certain, of course. Science rarely deals in absolutes. There's always room for new data, new theories, new insights. But as of right now, with the data we have, the void hypothesis is by far the best explanation for the Hubble tension. Take a moment to let that settle. Feel the weight of it, or perhaps more accurately, feel the lightness of it. We're floating in a cosmic underdensity, a region where the universe is less dense, more empty, more void-like than the average. It's a strange feeling, isn't it? To think that the darkness between stars, between galaxies, is even darker here than elsewhere. That we live in a relative desert of the cosmos. But what does that actually mean? What does it mean for space to be less dense? It's not like there's a hard boundary. It's not like we could fly in a spaceship and suddenly cross from the void into the denser regions beyond. The transition is gradual. As you travel outward from our position, you'd notice that galaxies gradually become more common. The great cosmic web of matter becomes denser, more interconnected. The voids become smaller, the filaments thicker. It's a gradient, not a wall. And we're not alone in here. 2 billion light-years is so vast that it contains thousands of galaxies. The Milky Way, Andromeda, all the members of the local group, the Virgo cluster, the Fornax cluster, and countless others all inhabit this underdense region. We're all in here together, floating in this cosmic bubble. But on average, if you picked a random point in space within this 2 billion light-year sphere, you'd be less likely to find a galaxy there than if you picked a random point elsewhere in the universe. Does this affect us? Does living in a void have any practical consequences for Earth, for the solar system, for life? The answer is almost certainly no. The density difference is tiny on local scales. Within the Milky Way, within the local group, even within the Virgo supercluster, things proceed just as they would anywhere else. Stars form, planets orbit, galaxies collide and merge. The void doesn't change these local processes. Its effect is only visible when you zoom out to cosmic scales, when you're measuring the overall expansion rate of space itself. But it does affect our observations. It affects what we see when we point our telescopes at the distant universe. And that has profound implications for cosmology. For decades, astronomers have been using relatively nearby observations to calibrate our understanding of the cosmos. We measure the properties of nearby supernovae and use them to understand distant ones. We observe the motions of galaxies in our vicinity and extrapolate to the universe as a whole. But if we live in an atypical region, if our local neighborhood isn't representative of the cosmic average, then those calibrations might be slightly off. Our cosmic measurements might have a systematic bias baked into them. This doesn't invalidate cosmology. Far from it. But it does mean we need to be more careful. We need to account for our position in a void when we make measurements. We need to use multiple independent methods to cross-check our results. And we need to be humble about the uncertainties in our knowledge. The universe is under no obligation to make itself easy for us to measure. The fact that we happen to live in an unusual location is just something we have to deal with. There's something poetic about this, though. Something fitting. Here we are, conscious beings on a small, rocky planet, looking out at the universe and trying to understand it. And we find ourselves in a void, a cosmic emptiness, a place where matter is scarce and darkness dominates. It's almost too metaphorically perfect. We're islands of complexity in an ocean of simplicity, pockets of order in a sea of entropy. And now we discover that we're literally floating in an underdense bubble of space-time. But let's go deeper. Let's explore what voids actually are, how they form, and what they tell us about the universe. Because the Portsmouth discovery is really just the beginning. It opens up an entire new way of thinking about our cosmic environment. Voids weren't always part of our picture of the universe. In the early 20th century, when astronomers first began measuring the distances to galaxies, they thought the universe was fairly uniform. Sure, there were local clusters of galaxies, places where they bunched together, but on large scales, everyone assumed that matter was distributed more or less evenly. This assumption even had a name, the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. Homogeneous meaning uniform, the same everywhere. Isotropic meaning the same in all directions. The first hints that this wasn't quite true came in the 1970s and 80s as astronomers began conducting large surveys of galaxy positions. One of the pioneering surveys was led by astronomers Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. They systematically measured the distances to thousands of galaxies in a thin slice of the sky, creating what's called a redshift survey. Redshift is a measure of how much a galaxy's light has been stretched by the expansion of the universe, which tells you how far away it is. When Geller and Huchra plotted their results, they were stunned. The galaxies weren't uniformly distributed at all. They formed patterns, long filaments, walls, sheets. And between these structures were vast empty regions. They called these regions voids, and one of the first they discovered was enormous. The Buddha's void, also known as the Great Void, spans about 330 million light-years in diameter and contains very few galaxies. Looking at their maps was like looking at soap bubbles. The galaxies outlined the surfaces of enormous bubbles, with empty space inside. This discovery revolutionized cosmology. Suddenly, the universe had structure on scales far larger than anyone had imagined. The cosmological principle needed to be refined. Yes, the universe is still homogeneous and isotropic on the very largest scales, averaged over billions of light-years. But on smaller scales, hundreds of millions to billions of light-years, it's anything but uniform. It's a cosmic web, a three-dimensional lattice of filaments and sheets, with voids in between. But how did this structure form? Why isn't the universe smoother? The answer lies in gravity and in the initial conditions of the universe right after the Big Bang. Even in the incredibly hot, dense, uniform plasma of the early universe, there were tiny fluctuations, quantum uncertainties, infinitesimal differences in density from one region to another. These fluctuations were stretched to cosmic scales during inflation, a brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. As the universe evolved, these tiny density differences grew. Regions that were slightly denser had slightly stronger gravity, which attracted more matter, which made them even denser. Regions that were slightly less dense lost matter to their denser neighbors, becoming even less dense. It's a runaway process. The dense regions collapsed into filaments and clusters. The underdense regions expanded and emptied out, becoming voids. Computer simulations of this process are remarkable. You can watch billions of years of cosmic evolution compressed into a few minutes of video. At first, everything looks nearly uniform, with just slight variations in density. But as time passes, the structure emerges. Filaments stretch across space. Clusters form at the intersections of filaments, and the voids grow and merge, becoming ever larger. By the present day, the simulation looks uncannily like the real universe. The cosmic web has formed naturally from those tiny initial fluctuations. And these voids aren't truly empty. They do contain some matter. There are a few lonely galaxies scattered through them, typically smaller and less active than galaxies in denser regions. There's also dark matter, the invisible substance that makes up most of the matter in the universe. Even in voids, dark matter exists, though at lower density. And there's dark energy, the mysterious force causing the expansion of the universe to accelerate. Dark energy, as far as we can tell, is truly uniform throughout space. It doesn't cluster like matter does. It fills the voids just as completely as it fills the densest clusters. Actually, some physicists think dark energy might be even more important in voids than elsewhere. Since voids have less matter and therefore less gravity to slow down expansion, dark energy's repulsive effect is more noticeable. Voids might be expanding faster than the denser regions, growing over time, claiming more territory. If this is true, then over the extremely long term, over trillions of years, the universe will become increasingly dominated by voids. The filaments and clusters will shrink to tiny islands in a vast ocean of emptiness. But we're getting ahead of ourselves. Let's focus on our void, this 2 billion light-year bubble we call home. How did it form? Is it unusual? The answer is complicated. Voids of this size aren't common, but they're not unheard of either. The largest known void, discovered in 2007, is called the Giant Void, or the Eridanus supervoid. It's about 1 billion light-years across, and was discovered because it corresponds to a cold spot in the cosmic microwave background, a region where the ancient light from the Big Bang appears slightly cooler than average. Astronomers think this cold spot is caused by the void's effect on light passing through it. As light travels through a void, it gets slightly sapped of energy by a phenomenon called the integrated Sachs-Wolf effect, leaving a faint imprint on the cosmic microwave background. Our void, at 2 billion light-years, would be larger than the Eridanus supervoid. That makes it rare, but not impossible. In a universe as vast as ours, even rare things happen somewhere. And we happen to be in one of those somewheres. It's a bit like a lottery. Any individual person is unlikely to win the lottery. But someone, somewhere, almost certainly will. We're the cosmic lottery winners, or perhaps losers, depending on how you look at it. We live in an unusual place. But here's something interesting. The Portsmouth team didn't just find evidence that we live in a void. They also calculated what properties this void would need to have to explain the Hubble tension. And it turns out the void would need to be quite underdense, about 20 to 30% less dense than the cosmic average. That's a significant deficit. It's on the edge of what's possible according to our models of cosmic structure formation. A void this large and this underdense is rare enough that some cosmologists initially questioned whether such a void could even exist. But subsequent analyses have been more favorable. Other teams have looked for evidence of our local underdensity in different ways, and several have found supporting signals. For example, the distribution of galaxies in large surveys shows hints of a local deficit. The number counts of galaxies as a function of distance suggest we might be in an underdense region. The peculiar velocities of nearby galaxies, the motions they have, in addition to the cosmic expansion, also show patterns consistent with living in a void. No single piece of evidence is conclusive on its own, but together they paint a compelling picture. And there's another implication that's worth considering. If we live in a void, and if that void is affecting our measurements of the Hubble constant, then the true value of the Hubble constant, the value you'd measure from an average location in the universe, might be different from what we've been calculating. It might be slower than our local measurements suggest. This would reduce or eliminate the Hubble tension. The cosmic microwave background measurements might be right. The supernova measurements might be biased by our position in a void. We've been arguing about which measurement technique is wrong, when actually both techniques might be right. They're just measuring different things. One measures the local expansion rate inside our void. The other measures the global expansion rate averaged over the entire universe. If this is true, it would resolve one of the biggest mysteries in cosmology. It would mean we don't need to invoke new physics or modify our theories. The universe behaves just as we thought it did. We were just confused because we didn't account for our atypical location. It's humbling in a way. All this sophisticated technology, all these brilliant minds, and we were tripped up by something relatively simple. We forgot to check if we were standing in an unusual place before we started measuring the universe. Of course, the void hypothesis isn't universally accepted yet. Science moves cautiously, especially when major claims are involved. Some cosmologists remain skeptical. They point out that creating a void as large and underdense as the one we're proposing is difficult in standard models. They argue that we'd need very specific initial conditions in the early universe to produce such a structure. Others note that if we live in a void, we should see other signatures of it. The cosmic microwave background should show a specific pattern on the sky. The distribution of galaxy types should be different inside and outside the void. Gravitational lensing, the bending of light by massive structures, should show characteristic signs. These are all valid points, and astronomers are actively investigating them. New surveys are mapping the cosmic web in ever greater detail. The Dark Energy Spectroscopic Instrument, DESI, is measuring distances to tens of millions of galaxies. The Euclid Space Telescope, launched by the European Space Agency, is mapping the shape and distribution of billions of galaxies. The Vera C. Rubin Observatory, currently under construction in Chile, will photograph the entire visible sky every few nights for a decade. All of this data will help us test the void hypothesis rigorously. And that's how science works. Someone proposes an idea. The idea makes predictions. Those predictions are tested. If the tests confirm the predictions, the idea gains support. If the tests contradict the predictions, the idea is modified or discarded. Right now, the void hypothesis is in that testing phase. It's a strong contender, perhaps the leading explanation for the Hubble tension. But it's not proven yet. We need more data, more analysis, more cross-checks. Imagine what it would mean, though, if it's confirmed. We'd have to redraw our mental maps of the cosmos. Textbooks would need updating. Our sense of place in the universe would shift subtly. We're not just on a planet orbiting a star in a galaxy. We're on a planet orbiting a star in a galaxy that's floating in an enormous cosmic void. It's one more layer of context, one more frame to put around our existence. And it raises fascinating questions. How many other civilizations might share this void with us? If intelligent life exists elsewhere, are they also in here, also puzzling over the Hubble tension from their own underdense perspective? Or are most civilizations located in the denser regions of the universe, where galaxies are more tightly packed and stars are more common? Is our void relatively empty of life? Or does life's rarity have nothing to do with cosmic density? We don't know. We don't even know if life exists elsewhere. But it's interesting to think about. If we ever detect signals from an alien civilization, one of the first things we might want to ask them is, where are you located in the cosmic web? Are you in a void like us? Or are you in a filament surrounded by galaxies? Their answer might tell us something profound about the conditions necessary for life to emerge and thrive. There's also a temporal dimension to consider. Voids evolve over time. They grow as the universe expands. Galaxies on the edges of voids gradually move inward, pulled by the gravity of the denser regions outside. But this process is slow, incredibly slow. Over the timescale of human history, even over the timescale of human civilization, voids don't change noticeably. But over millions or billions of years, they do. The void we inhabit now might have been smaller in the past. It might grow larger in the future. Galaxies that are now in denser regions might one day fall into the void. Or conversely, if the void's expansion slows or reverses, it might shrink, and we'd find ourselves in a denser environment. These changes happen on timescales so long that they're almost impossible to fathom. Millions of years, tens of millions, hundreds of millions. By the time our void structure noticeably changes, humanity will likely be long gone, evolved into something unrecognizable or extinct entirely. The Earth itself might be gone, swallowed by the sun as it expands into a red giant in about 5 billion years. So from a practical standpoint, the evolution of our void is irrelevant to us. But from a cosmic perspective, it's all part of a great slow dance, the reshuffling of matter and energy that's been going on since the Big Bang and will continue until the universe ends, if it ever does. Speaking of the end of the universe, living in a void might affect our ultimate fate, at least locally. If voids expand faster than denser regions, and if dark energy continues to push the universe apart, then eventually the void might become completely isolated. Galaxies outside the void would recede beyond our cosmic horizon, the distance beyond which light can no longer reach us, because space is expanding faster than light can travel. We'd be cut off, isolated in an island of space that's causally disconnected from the rest of the universe. This is a far future scenario, trillions of years from now, but it's worth contemplating. In that distant era, any civilizations still existing in our void would look out and see only the other galaxies within the void. Everything else would have disappeared over the horizon. They would have no way to know that a larger universe existed beyond their bubble. To them, the void would be the entire universe. They'd rediscover cosmology from scratch and conclude that the universe is finite, containing only the few thousand galaxies visible to them. They'd be wrong, of course, but they'd have no way to know it. The true scale of the cosmos would be forever hidden from them. It's a sobering thought. We live in a privileged time, cosmologically speaking. The universe is old enough that structures have formed, galaxies and stars and planets, but it's young enough that the expansion hasn't yet carried distant galaxies beyond our horizon. We can still see the cosmic microwave background, that ancient light from the Big Bang. We can still map the large-scale structure of the universe, but this window won't stay open forever. Eventually, billions of years from now, the expansion will accelerate to the point where most of the universe becomes invisible. Future astronomers will have a much more limited view of the cosmos, unless, of course, dark energy changes. And that brings us to another layer of mystery, one that intertwines with our void story in unexpected ways. Remember earlier when I mentioned that the expansion rate of the universe seems to be different in different places, and that living in a void might explain this difference? Well, there's another possible explanation that's been gaining attention recently. What if dark energy itself isn't constant? What if it's evolving over time? This idea is controversial, but intriguing. For most of the history of cosmology, dark energy was assumed to be constant, a property of empty space itself. Einstein's cosmological constant, lambda, was the simplest explanation. But recent observations, particularly from the dark energy spectroscopic instrument, have hinted that dark energy might not be constant. It might be weakening over time. If that's true, it could also help explain the Hubble tension. Maybe the expansion rate was faster in the recent past and is now slowing down. Our local measurements, which look at relatively nearby and recent supernovae, would reflect the faster expansion. Measurements from the cosmic microwave background, which look back to the early universe, would reflect a different phase of dark energy's evolution. But here's the fascinating part. The void hypothesis and the evolving dark energy hypothesis might both be true. They're not mutually exclusive. We could live in a void, and dark energy could be evolving. In fact, some researchers think that voids might be where dark energy's effects are most visible. If dark energy is weakening or changing, voids might be the first places we'd notice, because that's where its influence is least diluted by the gravitational pull of matter. This is all speculative, of course. We're at the frontier of knowledge here, the place where science becomes a conversation, where different ideas compete and combine, where data is still ambiguous enough that multiple interpretations are possible. In 10 years, we'll probably have a much clearer picture. New telescopes, new surveys, new theoretical insights will clarify things. But right now, in this moment, we're in that wonderful and frustrating place where the universe is revealing its secrets slowly, piece by piece, and we have to be patient. So let's pause here. Take a breath. Notice how you're feeling. Is your body relaxed? Is your mind wandering in that pleasant way that happens as sleep approaches? We've covered a lot of ground already. We've discovered that we live in a void, a cosmic underdensity 2 billion light-years across. We've explored what voids are, how they form, and why our void might explain the Hubble tension. We've touched on the implications for our understanding of the universe and our place in it. Let's dive deeper into the evidence itself. How exactly do sound waves from 13 billion years ago tell us we're living in a void? It's a remarkable piece of detective work, one that combines observation, theory, and sophisticated data analysis in ways that would have seemed like science fiction just a few decades ago. Remember those baryon acoustic oscillations we talked about earlier? Those frozen sound waves imprinted on the distribution of galaxies. They're the key to everything. To understand how they work as a measuring tool, imagine you're standing in a field at night, and in the distance you see lights. You want to know how far away those lights are, but you have no direct way to measure the distance. However, you know something useful. You know that all the streetlights in this area are exactly the same height. So if you can measure how tall a light appears to be from your perspective, you can calculate how far away it must be. The smaller it appears, the farther away it is. Astronomers call this a standard ruler. Baryon acoustic oscillations give us exactly that, a standard ruler imprinted on the cosmos. We know from theory and from observations of the cosmic microwave background that these sound waves traveled a specific distance before they froze, about 490 million light-years in today's expanded universe. So, when we look at the distribution of galaxies and measure how far apart they tend to be, we're seeing that standard ruler. If galaxies appear to be separated by the expected distance, then space is expanding at the rate we'd expect. But if they appear closer together or farther apart than they should be, that tells us something interesting is happening with the expansion rate in that region. This is what the Portsmouth team did, but on an enormous scale. They used data from multiple galaxy surveys, including the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument. These surveys have measured the positions and distances of millions of galaxies across a huge volume of space, creating a three-dimensional map of the cosmic web. By analyzing this map and looking for the baryon acoustic oscillation signal, they could measure the expansion rate in our local region of the universe with incredible precision. And what they found was subtle but significant. The baryon acoustic oscillation scale appeared slightly different in our local region compared to what you'd expect from the global average. Galaxies in our vicinity were separated by distances that suggested space was expanding slightly faster here than the cosmic average would predict. Not dramatically faster. We're talking about a difference of a few percent. But that few percent difference is enough to explain the entire Hubble tension. Now, a few percent might not sound like much, but in cosmology, precision matters enormously. The Hubble constant, that number describing how fast the universe is expanding, has been measured to within a few percent accuracy by multiple methods. When two precise measurements disagree by a few percent, that's a real problem. It means something fundamental is wrong with either our measurements or our understanding. The void hypothesis resolves this by saying that both measurements are correct. They're just measuring different things. One measures the local expansion rate inside our void. The other measures the global average. The difference between them tells us how underdense our void is. But how underdense does a region need to be to create this effect? This is where the calculations get interesting. The Portsmouth team modeled different void scenarios, testing how large and how empty a void would need to be to produce the observed Hubble tension. They found that a void about 2 billion light-years across, with a density about 20 to 30% below the cosmic average, would do the trick. Anything smaller or less underdense wouldn't create a big enough effect. Anything larger or more underdense would create too big an effect and would also be inconsistent with other observations. 20 to 30% underdense might not sound dramatic, but remember, we're talking about averaging over enormous volumes of space. Even a void contains galaxies, dark matter, dark energy, all the usual cosmic ingredients. It's just that when you add it all up and average it over billions of light years, there's about 20 to 30% less matter than you'd find in a typical region. That's enough to affect the expansion rate measurably, but not so much that the void would stand out as an obvious anomaly in other observations. And this is important. The void can't be too extreme, or we would have noticed it already in other ways. For example, the cosmic microwave background should look slightly different if we're in a void. Light traveling through underdense regions gets affected by something called the integrated Sachs-Wolf effect. As light passes through a void, it falls into the gravitational potential well at the void's edge, gains energy, travels through the relatively flat interior, and then climbs out of the potential well on the far side. Normally, the energy gained falling in would be exactly balanced by the energy lost climbing out. But because the universe is expanding and dark energy is pushing things apart, the potential well becomes shallower while the light is in transit. So the light ends up losing a bit of energy overall, making it appear slightly colder. If we're near the center of a 2 billion light-year void, we should see this effect as a slight cold spot in the cosmic microwave background in the direction opposite to where the void extends. Some researchers have looked for this signal, and the results are intriguing but not conclusive. There are hints of a cold spot, but the signal is noisy and could be explained by statistical fluctuations. This is an active area of research, and future observations with better instruments might clarify things. Another way to test the void hypothesis is to look at the distribution of different types of galaxies. Galaxies in voids tend to be different from galaxies in denser regions. They're often smaller, less massive, and less actively forming stars. This makes sense because void galaxies have less interaction with neighbors, fewer mergers, less gas inflow from the cosmic web. They're cosmic hermits, isolated and quiet. If we're in a large void, we should see an excess of these quiet void-type galaxies in our local region compared to the cosmic average. Some studies have found hints of this, but again, the signal is subtle and requires careful analysis. There's also the question of our motion through space. The Milky Way isn't stationary. It's moving relative to the cosmic microwave background at about 600 kilometers per second. This motion is caused by the gravitational pull of nearby structures, the Great Attractor, the Shapley supercluster, and other massive concentrations of galaxies. If we're in a void, our motion should reflect the distribution of matter around us. We should be moving away from the center of the void and toward the denser regions beyond. Analyzing the pattern of peculiar velocities of nearby galaxies could test this prediction. Some preliminary studies suggest our motion is consistent with living in a void, but more data is needed for a definitive answer. All of these tests are ongoing. Astronomy moves slowly because the universe is big and gathering data takes time. Telescopes need years to survey the sky. Analyzing millions of galaxy spectra requires enormous computational resources. Cross-checking results, eliminating systematic errors, testing alternative explanations. All of this takes years of painstaking work by hundreds of researchers around the world. But that's how science advances. Not through sudden revelations, but through the gradual accumulation of evidence, the slow construction of an increasingly accurate picture of reality. And while this work continues, we can contemplate what it means to live in a void. There's something almost meditative about it. Close your eyes for a moment and picture it. You're floating in darkness, all around you, in every direction, mostly emptiness. Here and there, faint points of light, galaxies, but they're far apart, separated by hundreds of millions of light years of nearly empty space. You're in the interior of an enormous bubble, so large that light takes 2 billion years to cross it. The walls of the bubble, where matter is denser and galaxies cluster together, are so far away that you can barely perceive them. You're adrift in cosmic silence, in the still heart of nothingness. But you're not alone. The Milky Way galaxy is here with you, 300 billion stars spiraling through space. Andromeda is here too, our sister galaxy, currently approaching us and destined to collide with the Milky Way in about 4 billion years. The collision will be spectacular, a slow-motion dance of gravity that will reshape both galaxies into something new. But even that cataclysm will happen here in the void, in this quiet, underdense corner of the universe. The void will barely notice. It's too vast, too empty to be affected by the merger of two galaxies. There are other galaxies here too. The local group contains about 80 members, most of them small dwarf galaxies orbiting the Milky Way or Andromeda. The Virgo cluster, about 50 million light-years away, contains over 1,000 galaxies clustered around the giant elliptical galaxy M87. The Fornax cluster, the Eridanus cloud, the Leo spur, all of these structures exist within our void. Thousands of galaxies total, scattered across 2 billion light-years. It sounds like a lot until you remember that in a denser region of the universe, a volume this size might contain tens of thousands or even hundreds of thousands of galaxies. We're in a relative desert. But deserts have their own beauty. There's a stark elegance to emptiness, a simplicity that allows you to see clearly. Maybe living in a void has advantages. Less clutter, less confusion. Fewer galaxies means each one stands out more clearly. When ancient humans looked up at the night sky, they could see thousands of stars because they lived in places with little light pollution. The darkness allowed the light to shine through. Maybe cosmic darkness works the same way. The emptiness of the void allows the few galaxies within it to be seen more clearly, studied more easily. Perhaps our cosmological insights are partly due to our position in an underdense region where the signal isn't drowned out by noise. Or maybe that's just romantic thinking. Maybe there's no advantage to living in a void, no cosmic purpose to our location. Maybe it's pure chance, random luck, the roll of the cosmic dice. The universe doesn't care where we are. It doesn't arrange itself for our convenience. We evolved here, on this planet, in this galaxy, in this void, because this is where the conditions happen to be right for life. If we'd evolved somewhere else, in a denser region, we'd be having the same thoughts about that location. We'd be wondering what it means to live surrounded by galaxies, what advantages that might bring, what disadvantages. The meaning we find in our cosmic address is meaning we bring to it. The void itself is indifferent. Still, there's something compelling about the symmetry. We're biological islands in a void of lifelessness, at least as far as we know. We're conscious beings in a universe that's mostly unconscious. We're pockets of order and complexity in an ocean of simplicity and entropy. And now we find out we're literally living in a void, a bubble of underdensity in the cosmic foam. It's as if the universe is reflecting our existential condition back at us through the structure of space-time itself. But let's return to physics. Let's talk about what voids tell us about the universe's evolution and ultimate fate. Voids aren't static. They grow over time as the universe expands. In the early universe, shortly after the Big Bang, there were no voids, or at least no large ones. The density fluctuations existed, the seeds of future structure, but they hadn't had time to grow yet. As millions and billions of years passed, gravity amplified those fluctuations. Dense regions collapsed and pulled matter inward. Underdense regions expanded and pushed matter outward. The rich got richer, the poor got poorer, and the voids grew. Computer simulations of this process show that voids start small and irregular, but gradually become larger and more spherical. Small voids merge into larger ones, just like soap bubbles coalescing. By the present day, about 13.8 billion years after the Big Bang, the cosmic web has reached a kind of mature state. There are still filaments connecting clusters, still voids between them, but the overall structure has stabilized, at least temporarily. Over the next few billion years, voids will continue to grow, but slowly. The structure we see today won't change dramatically over human timescales, or even over the lifetime of the sun. But look farther into the future, and things get interesting. Dark energy is causing the expansion of the universe to accelerate. This acceleration has been going on for the past few billion years, and as far as we can tell, it will continue indefinitely. As the universe accelerates, the expansion rate increases, space stretches faster and faster, and structures become increasingly isolated. Galaxies that are currently outside our cosmic horizon, already unreachable, will be joined by more and more galaxies as they recede beyond the point where light from them can ever reach us again. Voids will expand, along with everything else, but they'll expand faster than denser regions because there's less gravity to resist the expansion. Eventually, in hundreds of billions of years, even galaxies within the same cluster will begin to separate. The Virgo cluster will disperse. The local group might hold together for a while longer because its members are bound by mutual gravity, but eventually, even those bonds might weaken. The Milky Way and Andromeda, having merged into a single galaxy, might find themselves increasingly alone as neighboring galaxies recede into the darkness. In 1 trillion years, the night sky would look very different from our perspective, assuming anyone or anything is still around to look at it. Most galaxies would have disappeared over the cosmic horizon. The cosmic microwave background would have cooled and redshifted so much that it would be essentially undetectable. The universe would appear nearly empty, a few nearby galaxies in an ocean of darkness. And any cosmologists living in that era, if such beings exist, would have a very difficult time reconstructing the history and structure of the universe. Most of the evidence would be gone, hidden beyond the horizon, or faded into invisibility. This is one of the strange features of dark energy's dominance. It erases information. It takes parts of the universe that were once visible and makes them permanently invisible. It's a kind of cosmic censorship, a horizon beyond which we cannot see and will never be able to see, no matter how long we wait or how powerful our telescopes become. This has philosophical implications. It means that our current understanding of cosmology, built on observations of the cosmic microwave background and the large-scale structure of the universe, is time-limited. Future civilizations won't have access to the same evidence we have. They'll have to trust our records, our data, our conclusions. Or they'll have to build their cosmology from scratch, using whatever limited information remains available to them. But that's the far future, trillions of years from now. In the more immediate future, over the next few million or billion years, the structure of the universe won't change dramatically. Voids will remain voids. Filaments will remain filaments. Our void will continue to be our void. And life, if it exists elsewhere in our void, will continue adapting to its cosmic environment just as we have. Which brings up an interesting question. Does living in a void affect the likelihood of life emerging? This is pure speculation, but it's worth considering. Life requires certain conditions: a stable star, a planet in the habitable zone, liquid water, organic chemistry, energy sources, time. None of these requirements directly depend on living in a void versus a dense region. Stars form in both environments. Planets form around stars in both environments. The fundamental chemistry and physics are the same everywhere, but there might be indirect effects. Voids have fewer galaxies, which means fewer stars, which means fewer planets, which means fewer opportunities for life to emerge. Just from a numbers perspective, you'd expect more life in denser regions simply because there are more possible sites for it to develop. On the other hand, denser regions might be more dangerous. More galaxies means more supernovae, more gamma-ray bursts, more radiation hazards. Galaxies in dense regions interact more, merge more often, triggering bursts of star formation and creating unstable environments. Maybe voids are safer. Maybe the quiet isolation of a void is actually conducive to the long-term stability that complex life requires. We don't know. We have a sample size of 1, life on Earth. We know it's possible for life to emerge in a void because here we are, but we don't know if life is more or less common in voids compared to elsewhere. We might not know until we detect life elsewhere and can survey enough sites to see patterns. Are civilizations more common in dense regions or in voids? Are technological species more likely to develop in quiet environments or in chaotic ones? These questions are unanswerable for now, but they're fascinating to think about. There's also the question of whether living in a void affects the psychology of any intelligent beings that evolved there. Would a civilization that evolved in a dense region, surrounded by thousands of nearby galaxies, have a different worldview from one that evolved in a void? Would they feel more connected to the cosmos, more aware of their place in a larger structure? Or would they feel overwhelmed, insignificant, lost in the crowd? Conversely, would a void civilization like ours feel isolated, lonely, special in its solitude? Or would we not notice at all because the cosmic environment is just the background we evolved in and take for granted? Humans have always projected meaning onto the cosmos. Ancient cultures saw gods and heroes in the stars. Medieval cosmology placed Earth at the center of a divinely ordered universe. Modern cosmology sees a vast impersonal mechanism governed by physical law. But even modern cosmology isn't free from interpretation. The way we talk about the universe, the metaphors we use, the significance we assign to discoveries, all of this is shaped by our culture, our psychology, our position in space and time. Living in a void might not affect our physics, but it might affect our philosophy. It might influence how we think about isolation and connection, emptiness and fullness, the rare and the common. Or maybe I'm overthinking it. Maybe a void is just a void, a region of slightly below average density with no deeper meaning. The universe doesn't care about meaning. It just exists, following the laws of physics from moment to moment, evolving according to the initial conditions set by the Big Bang, and the subsequent interplay of gravity, dark matter, dark energy, and ordinary matter. We're the ones who care about meaning. We're the ones who look at the structure of the cosmos and ask what it means for us. The cosmos itself is silent on the subject. But even if the cosmos is silent, the questions remain interesting, and they connect to deeper questions about cosmology and the nature of the universe. For instance, why does the universe have structure at all? Why isn't it perfectly smooth? The answer, as we discussed earlier, lies in quantum fluctuations during the inflationary period right after the Big Bang. But why those particular fluctuations? Why that particular pattern of density variations? Was it random chance? Or was there some underlying principle that determined the initial conditions? This is one of the deepest questions in cosmology, and we don't have a complete answer. Inflation theory predicts that quantum fluctuations would be stretched to cosmic scales, creating a spectrum of density variations across a wide range of scales. The predictions of inflation match observations remarkably well. The cosmic microwave background shows exactly the pattern of hot and cold spots that inflation predicts. The distribution of galaxies on large scales matches the power spectrum that inflation predicts. So inflation seems to be correct, at least in its broad outlines. But inflation doesn't tell us why the universe inflated in the first place. It doesn't explain what caused inflation to start or what caused it to stop. These are questions that push beyond our current theories into the realm of speculation. Some physicists think inflation is eternal. that it's always happening somewhere in a larger multiverse, creating countless bubble universes, each with its own set of physical laws and initial conditions. In this view, our universe is just one bubble among many, and the structure we observe is just one possible outcome of the quantum randomness inherent in the inflationary process. If that's true, then our void, our particular pattern of cosmic structure, is just one possibility that happened to be realized in our bubble. In other bubbles, other patterns exist. Some might have more voids, some might have fewer. Some might have different sizes of voids, different distributions of matter, and in a vast enough multiverse, every possible arrangement exists somewhere. We live in a bubble with a 2 billion light-year void because that's one of the possible arrangements, and we happen to be in the part of the multiverse where it was realized. This is heady stuff, and it's highly speculative. The multiverse hypothesis is controversial because it's difficult or impossible to test. If other bubble universes exist, they're causally disconnected from ours. We can't observe them, can't communicate with them, can't gather data about them. So in what sense is the multiverse a scientific theory rather than just a metaphysical speculation? This debate continues, and not all physicists accept the multiverse idea. But it's one possible answer to the question of why our universe has the structure it does. Alternatively, maybe there's no multiverse. Maybe our universe is all there is, and the initial conditions were set by some principle we don't yet understand. Maybe there's a theory of everything, a final, unified description of physics that predicts the exact pattern of density fluctuations that led to the structure we observe. Maybe in the future, physicists will write down equations that explain why voids like ours exist, why they have the size and density they do, why the cosmic web has the particular architecture it has. That would be deeply satisfying, a genuine understanding of why the universe is the way it is, rather than just a description of how it is. But we're not there yet. We're still in the phase of gathering data, testing hypotheses, building models. The void hypothesis is part of that process. It's an attempt to explain specific observations using known physics. It doesn't require new particles or forces. It doesn't invoke the multiverse or exotic theories. It just says we live in an underdense region, and that underdensity affects our measurements. Simple, elegant, testable. That's what makes it appealing. And if it's confirmed, it will join the long list of discoveries that have reshaped our understanding of our cosmic address. We're not at the center of the solar system. We're not at the center of the galaxy. We're not in a special galaxy. We're not even in a typical region of the universe. We're in a void, floating in underdensity, our view of the cosmos subtly skewed by our atypical location. It's one more step in the long process of decentering humanity from the cosmic picture. And yet, paradoxically, it also makes us slightly special. Not special in a privileged sense, but special in the statistical sense. We're in an unusual place. Not impossible, not unique, but uncommon. There's a parallel here with the anthropic principle, the idea that the universe appears fine-tuned for life, because if it weren't, we wouldn't be here to observe it. You can only observe a universe that's compatible with your existence. Similarly, we can only observe the universe from locations where observers can exist. If voids are less conducive to life than dense regions, then most observers in the universe wouldn't live in voids. They'd live in filaments and clusters where galaxies are abundant and stars are common. The fact that we live in a void might tell us something about the conditions necessary for life, or it might just be a statistical accident, a roll of the dice that happened to come up with this particular outcome. We won't know unless we find other life. If we detect civilizations elsewhere and can determine where they're located in the cosmic web, we'll start to get statistical data. Are most civilizations in voids, or are most in dense regions? Is there a correlation between cosmic environment and the likelihood of developing technology, intelligence, radio transmissions? These are questions for the far future, assuming humanity survives long enough to answer them. For now, they're just intriguing possibilities, thought experiments to occupy our minds as we drift toward sleep. And speaking of sleep, Notice how your body feels now. Are you relaxed? Is your breathing slow and steady? The mind wanders when it's ready to sleep, following tangents, exploring connections, losing the thread, and finding it again. That's natural. That's how consciousness transitions from wakefulness to dreams. The structure of thought becomes looser, more associative, less concerned with logic, and more concerned with feeling and image. The void becomes not just a physical thing, but a metaphor, an emotional space, a way of thinking about emptiness and presence, isolation and connection. We live in a void, but the void isn't empty. It contains galaxies, stars, planets, life, consciousness, thought. It contains everything we've ever known or experienced. From our perspective, the void is the universe. It's only from an outside perspective, from the vantage point of cosmology, that we can see it as a void, as an underdensity in the larger structure. And even then, the difference is just 20 or 30%. If you filled the void with matter until it reached average density, you'd only need to add one more galaxy for every 3 or 4 that are already here. It's not a huge difference. Not like the difference between a galaxy and intergalactic space, where the density contrast is 1,000,000 to 1 or more. It's subtle, a gentle underdensity, a soft void. Maybe that's why it took so long to discover. The signals are subtle. The difference is small. You need precise instruments, large surveys, sophisticated analysis. You need to compare local measurements with global ones and notice the discrepancies. It's detective work, piecing together clues from multiple sources, testing hypotheses against data. The scientific method in action, the slow, patient accumulation of knowledge that's been going on for centuries and will continue for centuries more. And in the meantime, we live our lives here in the void. We wake up, go about our days, look up at the stars occasionally, wonder about our place in the universe. The void doesn't change that. It doesn't affect the price of bread, or the laughter of children, or the feel of rain on skin. It's a cosmological fact, interesting and important for understanding the universe on large scales, but not directly relevant to daily life. And yet, knowing it changes something. Knowing that we're in a void, that our cosmic neighborhood is unusual, that the structure we see when we look out at the universe is shaped by our atypical location. It adds a layer of context to our existence. It's one more frame around the picture, one more way of understanding where we are and how we got here. So let's explore that further. Let's look at other voids in the universe and see how ours compares. Let's understand the full cosmic landscape, the foam structure of reality, and what it tells us about the universe's past and future. Because our void isn't unique. It's unusual, perhaps larger and more underdense than most, but it's not the only void in existence. The universe is full of them, scattered throughout the cosmic web like bubbles in champagne. The first void ever discovered, the Buddha's void, was found in 1987 by Robert Kirshner and his colleagues. They were conducting a survey of galaxy redshifts, measuring distances to hundreds of galaxies in a particular region of the sky, in the constellation Boötis. And they noticed something strange. There was a large region, about 330 million light-years across, that contained hardly any galaxies at all. They expected to find around 10,000 galaxies in that volume, based on the average density of the universe. Instead, they found only about 60. That's less than 1% of the expected number. At first, they thought it might be an error. Maybe their survey was incomplete in that region. Maybe dust or some other foreground object was blocking their view. But further observations confirmed it. The void was real. It was genuinely empty, or nearly so. The few galaxies that did exist in the void were mostly small, faint, and showed little signs of active star formation. They were cosmic hermits, isolated and quiet in the vast darkness. The discovery of the Buddha's void was shocking at the time. It challenged the assumption that the universe was relatively uniform on large scales. How could such a large empty region exist? What created it? What happened to all the matter that should have been there? These questions drove decades of research into cosmic structure formation, leading to our current understanding of how gravity and dark energy shape the cosmic web. Since then, astronomers have discovered many other voids. The local void, which is relatively close to us, about 150 million light-years across. The Capricornus void, the Sculptor void, the Eridanus supervoid, which we mentioned earlier, about 1 billion light-years across, and notable because it corresponds to a cold spot in the cosmic microwave background. Each void has its own characteristics, its own size, its own degree of underdensity. But they all share the same basic nature. They're regions where galaxies are rare, where the cosmic web is sparse, where darkness dominates. The sizes vary considerably. Small voids might be only 30 to 50 million light-years across. Medium voids, the most common type, range from 100 to 300 million light-years. Large voids, like the Buddha's void, reach 3 to 400 million light-years. And supervoids, the rarest and largest structures, can exceed 500 million to 1 billion light-years. Our Cetus Chronosto void, at 2 billion light-years, would be at the extreme end of the distribution. Not impossible according to theory, but definitely unusual. Only a small percentage of voids would be expected to reach this size. The shapes of voids are also interesting. Small voids tend to be irregular, elongated, or fragmented. But as voids grow larger, they become more spherical. This is because gravity tends to pull matter inward from all directions equally, creating a symmetric structure. By the time a void reaches several 100 million light-years across, it's usually quite round. Our void, if it exists as theorized, would likely be fairly spherical given its enormous size. We'd be somewhere inside a cosmic bubble, with the densest regions of matter forming a kind of shell around us at the edges. But remember, these boundaries aren't sharp. Voids don't have walls. The transition from underdense to average density to overdense happens gradually, over tens or hundreds of millions of light-years. It's like walking from a valley into hills and then into mountains. There's no single point where you cross from one to the other. It's a continuous change. Similarly, as you travel from the center of a void outward, you'd gradually encounter more and more galaxies. The cosmic web would become denser, more connected, more vibrant with activity. The interiors of voids aren't completely empty, as we've discussed. There are always some galaxies, typically a few percent of what you'd find in an average region. These void galaxies are fascinating in their own right. They tend to be late-type spirals, or irregular galaxies, often blue in color indicating active star formation. This might seem counterintuitive. You'd think isolated galaxies would run out of gas and stop forming stars. But actually, void galaxies can be quite efficient at star formation because they're left alone. They don't get their gas stripped away by interactions with neighbors. They don't undergo disruptive mergers. They just peacefully convert their gas into stars over billions of years. Some void galaxies are also unusually dark matter rich. This is inferred from their rotation curves, the relationship between their rotational velocity and radius. Void galaxies often rotate faster than you'd expect based on their visible matter, suggesting they're embedded in more massive dark matter halos than galaxies in denser regions. Why this would be is still debated. Perhaps dark matter halos in voids retain more of their mass because there are fewer tidal interactions to strip it away. Or perhaps there's a selection effect where only galaxies with particularly massive halos can form in voids in the first place. There are also cosmic rays to consider. Cosmic rays are high-energy particles, mostly protons, that travel through space at nearly the speed of light. They're produced by supernovae, active galactic nuclei, and other energetic events. In dense regions of the universe, cosmic rays are more common because there are more sources producing them. In voids, cosmic ray flux is lower. This has implications for any life that might exist in void galaxies. Lower cosmic ray flux means less radiation exposure, which might make void environments slightly safer for life. On the other hand, cosmic rays play a role in chemistry and cloud formation in planetary atmospheres, so their absence might have complex effects that aren't entirely beneficial. The magnetic fields in voids are also weaker than in denser regions. Magnetic fields in the universe are generated by moving charged particles, and they're amplified by turbulence and dynamo processes in galaxies and galaxy clusters. In voids, with fewer galaxies and less activity, magnetic fields are correspondingly weaker. This affects how charged particles move through intergalactic space, how radio waves propagate, and potentially how large-scale structure forms over very long timescales. But let's zoom out again. Let's look at the entire cosmic web and see how voids fit into the larger picture. Imagine you could see the universe from outside, from some impossible vantage point where you could perceive the positions of all galaxies simultaneously. What would you see? You'd see filaments, long chains of galaxies stretching across hundreds of millions of light years. These filaments would connect at nodes, dense clusters where thousands of galaxies gather. The Virgo cluster, the Coma cluster, the Shapley supercluster, these are examples of nodes in the cosmic web. Between the filaments, you'd see voids, enormous bubble-like regions with very few galaxies. The filaments outline the voids, forming a three-dimensional network that looks remarkably like biological structures. Neural networks in the brain, mycelial networks of fungi, circulatory systems. The cosmic web has a similar architecture, suggesting that perhaps there are universal principles of network formation that apply across vastly different scales and contexts. Or perhaps it's just a coincidence, pattern matching by human minds eager to find connections and meaning. The cosmic web formed naturally from the initial density fluctuations in the early universe. Computer simulations have reproduced this structure with remarkable accuracy. You start with a nearly uniform distribution of dark matter particles. Add tiny density variations matching the observed spectrum from the cosmic microwave background, and let gravity do its work. Over billions of simulated years, the dark matter collapses along preferred axes, forming sheets first, then filaments, then clusters at the intersections of filaments. Ordinary matter follows the dark matter, falling into the gravitational potential wells and forming galaxies where the dark matter is densest. The voids emerge automatically from this process. They're simply the regions that were slightly underdense to begin with. As matter falls out of these regions and into the surrounding overdense areas, the voids grow and become more underdense. It's a self-reinforcing process. The more matter leaves, the weaker the gravity, the faster the remaining matter leaves. Eventually, you reach an equilibrium where the voids contain just a few percent of the matter they started with, and almost all of it has migrated to the filaments and clusters. This process is still ongoing, but slowly. Voids continue to grow, but the rate of growth has slowed as the universe has aged. In the early universe, when everything was denser and closer together, structure formation was rapid. Voids expanded quickly, filaments collapsed quickly, clusters assembled quickly. But now, with the universe more spread out and dark energy dominating, the pace has slowed. Structure formation hasn't stopped, but it's proceeding more gradually. Galaxies still merge, clusters still grow, voids still expand, but all of it happens over longer timescales. In the far future, as dark energy continues to accelerate the expansion, structure formation will essentially cease. The voids will stop growing, not because they've reached some maximum size, but because space itself is expanding so fast that even the tenuous connections between structures will break. Galaxy clusters will become isolated islands in an ever-expanding sea of space. Eventually, even individual galaxies might start to lose their outer regions as expansion overcomes gravity on larger and larger scales. But that's trillions of years in the future, so far ahead that it's almost meaningless to contemplate. The universe we know, the universe of galaxies and stars and planets, will look very different by then if it still exists at all. But back to the present, or at least the observable universe as it exists now. The cosmic web is a snapshot of a process billions of years in the making. Every void, every filament, every cluster is a consequence of tiny quantum fluctuations in the first fraction of a second after the Big Bang. Those Fluctuations were stretched to cosmic scales by inflation, imprinted on the cosmic microwave background, and amplified by gravity over billions of years. The result is the universe we see today, a foam-like structure of matter and emptiness, light and darkness, the cosmic web stretching across billions of light years in all directions. And somewhere in this vast structure, we exist. The Milky Way, a fairly ordinary spiral galaxy, sits in an underdense region 2 billion light-years across. We're not at the center of the void, probably. There likely is no meaningful center. Voids are roughly spherical, but they're not perfect spheres, and they don't have a single point that you could identify as the exact center. We're somewhere within the void, that's all we can say, with confidence. Maybe closer to one edge, maybe more central. The data isn't precise enough yet to pin down our exact position within the structure. What would it look like if you could travel through the void? If you could somehow move at many times the speed of light and cross the 2 billion light-years from one side to the other? At first, starting from a dense region outside the void, you'd see galaxies all around you. The night sky would be rich with them, countless spirals and ellipticals in every direction. As you crossed into the void, you'd notice them becoming sparser. The galaxies would spread out, the distances between them increasing. The night sky would grow darker as fewer galaxies populated your field of view. Deep in the interior of the void, you'd be surrounded by darkness. Here and there, a faint smudge of light would mark a distant galaxy, but they'd be few and far between. You'd have a profound sense of isolation, of emptiness, of the vastness of space unobstructed by matter. Looking back toward the edge you came from, you'd see a concentration of galaxies on the horizon, a faint glow marking the denser regions beyond. Looking ahead toward the other edge, you'd see the same thing in the opposite direction, but in most directions, just darkness. And yet, even in this darkness, you wouldn't be in a true vacuum. Space is never truly empty. Even in the voids, there's still some matter. A few atoms per cubic meter perhaps, mostly hydrogen and helium left over from the Big Bang. There's dark matter, invisible but present, filling the void with its gravitational influence. There's dark energy, even more mysterious, pushing space apart. There are photons, particles of light, traveling through the void from distant sources. There are cosmic rays, neutrinos, gravitational waves, the pervasive cosmic microwave background radiation. The void isn't empty, it's just sparse, underdense, stretched thin. This distinction matters. A true vacuum, a region of space with absolutely nothing in it, is probably impossible to achieve. Even in the laboratory, in the best vacuum chambers we can build, there are always some particles, some fields, some quantum fluctuations. The universe doesn't do absolute emptiness. It does relative emptiness, regions where matter is rare compared to other regions. Voids are the largest and most empty regions that naturally occur, but they're still part of the cosmic web, still connected to the larger structure, still filled with the fundamental ingredients of the universe. There's also the question of what happens at the edges of voids. The boundaries between voids and filaments are regions of active galaxy formation and evolution. As gas flows from voids into filaments, it gets compressed and heated. This can trigger star formation, creating new galaxies, or adding mass to existing ones. Some of the most spectacular starburst galaxies, galaxies undergoing intense bursts of star formation, are found at the edges of voids, where infalling gas collides with the denser environment of the filaments. These boundary regions are also where galaxy harassment occurs. Galaxy harassment is a process where galaxies in clusters, or filaments, experience tidal forces and gravitational interactions with their neighbors. These interactions can strip away gas, trigger starbursts, and transform the morphology of galaxies. Spiral galaxies can be turned into ellipticals. Star formation can be quenched as gas is removed. In contrast, galaxies in the interior of voids are largely immune to harassment. They evolve in isolation, peacefully converting their gas into stars without external interference. This creates a kind of cosmic ecology, different environments, favoring different types of galaxies and different evolutionary paths. Voids select for isolated, gas-rich, star-forming spirals. Filaments and clusters select for interacting, gas-poor, quiescent ellipticals. The cosmic web isn't just a spatial structure. It's an environmental gradient, a landscape of different conditions that shape the galaxies within it. Understanding this landscape helps astronomers understand why galaxies look the way they do, why some are red and dead, while others are blue and alive with star formation. Our own Milky Way, living in a void, might have been shaped by this environment. Perhaps we're a gas-rich spiral, precisely because we've avoided the harassment and stripping that occurs in denser regions. Perhaps our leisurely rate of star formation, about 1 solar mass per year, is typical of void galaxies. Perhaps if we lived in a cluster, we'd have exhausted our gas supply billions of years ago and would now be a red elliptical, a galaxy of old stars with no new generations being born. Of course, this is speculative. The Milky Way's properties are determined by many factors, not just our location in the cosmic web. Our merger history, the mass of our dark matter halo, the efficiency of our stellar feedback processes, all of these play roles. But environment matters too. And living in a void is an environmental condition that likely has some effect on our evolution, even if we can't quantify exactly what that effect is. There's also the question of how long we've been in the void. Voids grow over time, so our void was smaller in the past. 2 billion years ago, it might have been only 1.5 billion light years across. 4 billion years ago, maybe 1 billion light years. Going back far enough, say to when the universe was only a few billion years old, our void might have been small enough that the Milky Way was closer to the denser regions. We might have experienced a different environment in our youth, more interactions, more nearby galaxies, before gradually drifting into the expanding void. This raises intriguing possibilities. Perhaps the Milky Way's history can be divided into phases based on our cosmic environment. An early phase, the first few billion years, when we were in a denser region and experienced more interactions. A middle phase, as the void grew, and we found ourselves in an increasingly isolated environment. And the current phase, deep in the void, largely alone, except for our companions in the local group. Each phase might have left traces in our structure, our stellar populations, our chemical abundances. If astronomers can decode those traces, they might be able to reconstruct our journey through the cosmic web over billions of years. Similar considerations apply to other galaxies in our void. Andromeda, the Virgo cluster, all the thousands of galaxies sharing this space with us. They've all been shaped by their environment, and that environment has been changing as the void has grown. The galaxies we see today are products not just of their internal processes, but of their cosmic context, the structure they're embedded in, the flows of matter and energy around them. And this connects to a broader theme in cosmology, the idea that you can't understand objects in isolation. A galaxy isn't just a galaxy. It's a galaxy in a particular environment, at a particular time, with a particular history. To fully understand it, you need to know its context, where it is in the cosmic web, how it got there, what it's been through. The universe is an interconnected whole, and every part influences every other part through gravity, light, and the flow of matter. This is one of the reasons cosmology is so challenging. You can't just study one thing at a time. You have to study everything at once, because everything is connected. The cosmic web shapes galaxies. Galaxies emit light and matter that affect the intergalactic medium. The intergalactic medium affects how light propagates and how structure forms. Dark matter provides the gravitational scaffolding for everything. Dark energy determines the expansion rate and the ultimate fate of structure. It's all linked together in a vast causal network spanning space and time. Our void is one node in that network. Understanding it requires understanding the initial conditions of the universe, the nature of dark matter and dark energy, the physics of galaxy formation, the evolution of structure over cosmic time. Every piece of data, every observation, Every theoretical insight contributes to the picture. And the picture is still incomplete. We're still gathering pieces, still fitting them together, still refining our understanding. But we've come a long way. 100 years ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Then Edwin Hubble discovered that the fuzzy nebulae in our telescopes were actually distant galaxies, island universes in their own right, and that the universe was expanding. That discovery revolutionized cosmology and set us on the path we're still following today. 50 years ago, we didn't know about dark matter or dark energy. We thought the universe was made of ordinary matter and radiation, and that its expansion was slowing down due to gravity. Then observations of galaxy rotation curves revealed dark matter, and observations of distant supernova revealed dark energy. Those discoveries revolutionized cosmology again, forcing us to admit that most of the universe is made of things we don't understand. 20 years ago, we didn't know about the Hubble tension. Our measurements seemed to agree. The expansion rate appeared to be well determined. Then more precise observations revealed the discrepancy, and we've been trying to figure out what it means ever since. The void hypothesis is the latest attempt to solve that puzzle, and it might turn out to be correct, or it might be replaced by something better as more data comes in. This is how science progresses. Not in a straight line, but in a spiral, circling back to old questions with new tools and insights, refining answers, discovering new mysteries even as old ones are solved. The process never truly ends. Every answer raises new questions. Every solved problem reveals new complexities. The universe is inexhaustible, and our curiosity is insatiable. And yet, despite all this complexity, there's a simplicity to the fundamental story. The universe began in a hot, dense state. It expanded and cooled. Quantum fluctuations created tiny variations in density. Those variations grew under gravity. Structure formed. Stars ignited. Planets coalesced. Life emerged. Consciousness arose. And now we look back at the universe that created us and try to understand it. We're the universe becoming aware of itself, asking questions about its own nature and history. Living in a void doesn't change that story. It's just a detail, a footnote about our particular location. But details matter. They add richness and texture to the narrative. They make the universe more interesting, more surprising, more full of unexpected twists. Who would have thought that we'd turn out to be living in an underdense bubble 2 billion light years across? Who could have predicted that this would help solve one of cosmology's biggest puzzles? The universe keeps surprising us, and that's part of what makes studying it so rewarding. Breathe slowly now. Feel your body relaxing deeper into rest. We've traveled far tonight, from our planet to our galaxy, to our void, to the cosmic web beyond. We've explored structure and emptiness, matter and dark energy, the beginning of the universe and its possible futures. And through it all, one theme emerges. The universe is vast, ancient, and full of wonders. And we're part of it, intimately connected to everything else, made of the same atoms that were forged in stars, governed by the same laws that shape galaxies. The void we live in is just one more wonder, one more unexpected feature of the cosmos. It's a reminder that the universe doesn't conform to our expectations. It's stranger and more subtle than we imagine. And there's always more to discover, always deeper layers to uncover, always new questions to ask. The journey of understanding never ends. It just continues, deeper and deeper, into the heart of mystery. Let's think about time for a moment. Time and how it relates to our position in this void. We often think of space and time as separate things, but Einstein showed us they're intimately connected. Space-time is a single fabric, curved by mass and energy, stretching as the universe expands. And in that expanding space-time, time itself flows differently in different gravitational environments. This is a real effect, not just theoretical. Clocks tick slower in strong gravitational fields. Time passes more slowly on the surface of the sun than it does in empty space. Time passes more slowly in a dense galaxy cluster than it does in a void. The differences are tiny, measured in nanoseconds over millions of years, but they're real and measurable. GPS satellites have to account for relativistic time dilation, or their positioning would drift off by kilometers. So in our void, where gravity is weaker than average, time actually flows slightly faster than it does in denser regions of the universe. Not by much. The difference is vanishingly small on human timescales, but over billions of years, over cosmic timescales, it adds up. An observer in our void would age slightly faster than an observer in a dense cluster, assuming both lived for billions of years and could somehow account for all other factors. The universe in our void would appear to evolve slightly faster. Stars would be born and die. Galaxies would rotate and merge, all proceeding at a pace that's imperceptibly quicker than the cosmic average. Does this matter? Probably not in any practical sense. The effect is far too small to influence anything meaningful. But it's another layer of complexity, another subtle way that our environment differs from other parts of the universe. We live in a region where not only space is underdense, but time itself flows at a slightly different rate. It's a poetic thought, even if the physical consequences are negligible. There's also the question of how voids affect the cosmic microwave background radiation that we observe. The cosmic microwave background is light from the early universe, photons that have been traveling through space for over 13 billion years. As these photons travel, they pass through various regions, dense clusters, filaments, voids, and each region leaves a slight imprint on the light. We mentioned the integrated Sachs-Wolf effect earlier. As light falls into a gravitational potential well, it gains energy and becomes bluer. As it climbs out, it loses energy and becomes redder. Normally, these effects cancel out, but in an expanding universe with dark energy, the potential wells become shallower over time. So photons that fall into a void when it's relatively dense, and then climb out later when it's become more underdense, end up losing energy overall. This makes those photons appear slightly colder, creating a cold spot in the cosmic microwave background. If we live in a large void, we should see evidence of this effect in the cosmic microwave background. There should be a hemispherical asymmetry, with one half of the sky appearing slightly colder than the other half. This would correspond to the direction where our void extends the farthest. Several research teams have looked for this signal, and the results are intriguing but not definitive. There are hints of asymmetry in the data, but the signal is noisy and could be explained by other factors. It's an active area of research, and future missions with better instruments might clarify the situation. The European Space Agency's Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background with unprecedented precision. The data from Planck has been analyzed in countless ways, looking for patterns, anomalies, anything that might reveal new physics. Some researchers have claimed to find evidence of our void in the Planck data. Others dispute this, arguing that the signals are too weak or could be artifacts of the analysis. This is typical of frontier science. The signals are subtle, the data is complex, and reasonable people can disagree about interpretation. But let's assume for a moment that the void hypothesis is correct and that future observations confirm it beyond doubt. What would that mean for cosmology going forward? How would it change the way we study the universe? First, it would mean we'd need to be more careful about local measurements. Any measurement made using relatively nearby objects, galaxies within a few 100 million light-years, would need to account for our position in the void. We'd need to apply corrections, adjusting our observations to account for the local underdensity. This isn't as simple as just adding a correction factor. It requires understanding the three-dimensional structure of the void, how density varies with position, how that affects different types of observations. Second, it would motivate more surveys of the large-scale structure. We'd want to map the void in detail, determine its exact size and shape, identify all the galaxies within it, measure their properties. This would require observing millions of galaxies, measuring their distances, their masses, their star formation rates. Projects like the Dark Energy Spectroscopic Instrument and the upcoming Vera Rubin Observatory are perfect for this. They're designed to survey huge volumes of space and create detailed three-dimensional maps. Third, it would spark renewed interest in theories of structure formation. How do voids this large form? Are they consistent with standard cosmological models, or do they require modifications? Some researchers have suggested that a void as large and underdense as ours might be difficult to explain with standard initial conditions. Maybe inflation needs to be tweaked. Maybe dark matter behaves slightly differently than we think. Maybe there are exotic physics at play. These speculations would drive theoretical work for years. Fourth, it would affect how we interpret observations of distant objects. When we look at quasars and galaxies billions of light years away, the light has traveled through various structures on its way to us. It's been gravitationally lensed by clusters, redshifted by the expansion, potentially absorbed and re-emitted by intergalactic gas. All of these effects depend on the structures the light passes through. If we're in a void, the light reaching us might be systematically different from light reaching an observer in a dense region. Accounting for this would require sophisticated modeling. Fifth, and perhaps most interestingly, it would make us question the cosmological principle in a new way. The cosmological principle states that the universe is homogeneous and isotropic on large scales, that there's no special location, no center, no preferred direction. This principle has been foundational to cosmology for a century. But if we live in a void large enough to affect our measurements, maybe the principle needs to be applied more carefully. Yes, the universe is homogeneous on very large scales, averaged over tens of billions of light years. But on smaller scales, a few billion light years, there's structure, and that structure matters. We can't just assume we're in a typical location. We need to check, using multiple independent methods. This is actually healthy for science. Assumptions should always be tested. The cosmological principle is a useful assumption, and it's probably true on the largest scales, but it shouldn't be taken on faith. It should be verified observationally. And if observations show that we're in an atypical location, we need to accept that and account for it. That's how science corrects itself, by confronting theories with data and adjusting when necessary. Now let's think about what happens if the void hypothesis turns out to be wrong. What if future observations rule it out? What if we find that we're not in a large void after all, or that the void isn't large enough to explain the Hubble tension? Then we'd be back to the drawing board, looking for other explanations. One alternative is that dark energy is indeed evolving, changing its strength over time. This is called quintessence, and it's been discussed for decades. Instead of being a constant, like Einstein's cosmological constant, quintessence is a field that varies with time and possibly with location. If quintessence is weakening, the expansion of the universe would have been faster in the recent past and is now slowing down. This could explain the Hubble tension without requiring us to live in a void. Another alternative is that there's some systematic error in one or both of the measurement methods. Maybe the supernova calibrations are off in some subtle way. Maybe there's dust absorption that we're not fully accounting for. Maybe the cosmic microwave background analysis has some unrecognized bias. Systematic errors are always a concern in precision measurements. And despite decades of work refining these techniques, it's possible something has been missed. A more exotic alternative is that gravity behaves differently on cosmic scales than general relativity predicts. Modified gravity theories have been proposed to explain various cosmological puzzles. Maybe the expansion rate depends on modified gravitational physics in ways we don't understand yet. This would be a revolutionary discovery, requiring a fundamental change to our understanding of physics, but it's not impossible. Or maybe the answer is some combination of factors. A small void plus slight evolution of dark energy plus minor systematic errors, all combining to create the observed Hubble tension. Real scientific puzzles often have complex answers rather than simple single-cause explanations. The universe doesn't owe us simplicity. But for now, the void hypothesis is the leading contender because it explains the observations without requiring new physics. It uses known structures, voids that we know exist, and applies them to solve a specific problem. Occam's razor, the principle that simpler explanations are generally preferred, favors the void hypothesis over more exotic alternatives. But Occam's razor is a guide, not a law. Nature might prefer complexity over simplicity. We won't know until we have more data. Let's shift perspective again and think about what living in a void might mean for the future of astronomy. As our telescopes improve and our surveys expand, we'll be able to map the cosmic web in ever greater detail. We'll identify every significant structure within billions of light years, every cluster, every filament, every void. We'll create simulations that reproduce the observed structure down to the smallest features, and we'll understand exactly where we sit in that structure, not just roughly in a void, but precisely positioned relative to all our cosmic neighbors. This detailed mapping will reveal patterns we can't yet see. Maybe there are superstructures beyond what we currently know, walls and filaments connecting multiple voids and clusters across scales of several billion light years. Maybe our void is part of a larger complex, a region of the universe that's systematically underdense compared to another region that's systematically overdense. Maybe there's a gradient across the observable universe, with density varying from one side to the other, and we just happen to be on the underdense side. These are speculative ideas, but they're testable. As we observe farther and map larger volumes, any such patterns would become visible. And if they exist, they'd raise even deeper questions. Why would the universe have such large-scale gradients? Are they consistent with inflation? Do they tell us something about the initial conditions? About the quantum fluctuations that seeded all structure? Or do they hint at physics beyond the standard model, some field or force that influenced structure, formation in ways we haven't considered? There's also the possibility of finding other voids as large as ours, or even larger. If our void is rare, but not unique, maybe there are a few others scattered across the observable universe. Observers in those voids would face the same Hubble tension we do. They'd be measuring a local expansion rate that differs from the global average. If we could somehow communicate with them, compare notes, we'd all realize we're in similar situations. We'd understand that the Hubble tension is a selection effect, a consequence of living in an unusual location. Of course, communicating across billions of light years is impossible with current technology and probably impossible in principle. Light from another void, billions of light years away, would take billions of years to reach us. And by the time it arrived, the expansion of space might have carried that void beyond our cosmic horizon. We're isolated by the vastness of space and the finite speed of light. But it's interesting to think about nonetheless. The universe might be full of civilizations, each in their own void, each puzzling over the same cosmological mysteries we face, never able to compare notes because the distances are too great. This isolation is one of the fundamental features of our universe. Space is so vast and light is so slow that most of the universe is forever out of reach. Even if we could travel at the speed of light, we could only ever visit a tiny fraction of the cosmos. The expansion of space ensures that distant galaxies are receding faster than light, carried away by the stretching of space-time itself. We can see them. Their light reaches us, but we can never go there. They're beyond an invisible boundary, called the cosmic horizon. And as time passes, that horizon shrinks. More and more galaxies slip over the edge, receding so fast that their light can no longer reach us. In 100 billion years, if any astronomers still exist, they'll look out and see only a handful of nearby galaxies. Everything else will have disappeared over the horizon. The cosmic microwave background will have cooled and redshifted into undetectability. Those future astronomers will have no way to know that the universe was once filled with hundreds of billions of galaxies. They won't be able to measure the Hubble constant, because there won't be enough distant objects to measure. They'll be cut off from cosmic history, unable to reconstruct the story we're telling now. This is sometimes called the information paradox of cosmology. Information about the universe's structure and history is being lost as the expansion accelerates. Future observers will have less data than we do. They'll live in a universe that appears smaller, simpler, and more mysterious. They might develop wildly incorrect cosmologies because the evidence for the correct cosmology has disappeared. They might think the universe is static, eternal, unchanging. They'd be wrong, but they'd have no way to know it. Unless, of course, they have records. If our civilization leaves behind detailed observations stored in some durable medium, future civilizations might find them and learn about the universe as it was billions of years ago. This is one motivation for archiving scientific data, not just for ourselves, but for hypothetical future beings who might want to know what the universe was like before it expanded beyond recognition. It's an act of cosmic generosity, leaving knowledge for descendants we'll never meet, in a future we can barely imagine. But this is getting far ahead of ourselves. Let's return to the present and think about what we can observe right now. One of the most exciting developments in recent years has been the advent of gravitational wave astronomy. In 2015, the LIGO detectors made the first direct detection of gravitational waves, ripples in spacetime caused by colliding black holes. Since then, dozens more events have been detected: black hole mergers, neutron star mergers, possibly other exotic sources. Gravitational waves offer a completely new way to observe the universe. Unlike light, which can be absorbed or scattered, gravitational waves pass through matter almost unaffected. They carry information directly from the source to us, unaltered by anything in between. And they're sensitive to the structure of spacetime itself, to the distribution of mass and energy along the path they travel. If we live in a void, gravitational waves passing through it might be subtly affected. The underdensity would create a slightly different spacetime curvature compared to a dense region. This could affect the propagation speed of gravitational waves, or their polarization, or their amplitude. The effects would be tiny, probably too small to detect with current instruments, but future detectors might be sensitive enough. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will be far more sensitive than current ground-based detectors. It might be able to detect subtle effects of large-scale structure on gravitational wave propagation. This would provide yet another independent test of the void hypothesis. If gravitational waves behave differently when passing through our local region compared to predictions based on average density, that would support the idea that we're in a void. And because gravitational waves are so fundamentally different from electromagnetic waves, this test would be almost completely independent of the baryon acoustic oscillation measurements, the supernova measurements, and the cosmic microwave background observations. Multiple independent lines of evidence all pointing to the same conclusion would be very convincing. There's also the possibility of using gravitational lensing to map the void. Gravitational lensing occurs when light from a distant object passes near a massive structure, and the structure's gravity bends the light's path. This can create multiple images of the same object, distort shapes, magnify brightnesses. By studying these effects, astronomers can map the distribution of mass, including dark matter, along the line of sight. If we're in a void, the lensing signal from distant objects should be weaker when the line of sight passes through the void compared to lines of sight through denser regions. The void's underdensity means less mass to bend the light, hence weaker lensing. Large surveys of galaxy shapes, called weak lensing surveys, could potentially detect this effect. The Euclid Space Telescope and the Rubin Observatory are both designed to conduct massive weak lensing surveys, observing billions of galaxies and measuring their shapes to incredible precision. Their data might reveal the three-dimensional structure of our void through its lensing signature. All of these different techniques, baryon acoustic oscillations, supernovae, cosmic microwave background, peculiar velocities, Gravitational waves, gravitational lensing, provide different perspectives on the same question. Where are we in the cosmic web? How dense is our local region? How does it compare to the global average? By combining data from all these sources, astronomers will build a comprehensive picture. It's like solving a jigsaw puzzle, where each technique provides a few pieces. Individually, the pieces might be ambiguous or unclear, but put them all together, and the full picture emerges. This is how modern cosmology works. It's intensely collaborative, drawing on data from dozens of telescopes and satellites, analyzed by hundreds of research groups around the world. No single observation or measurement settles anything. It's the accumulated weight of evidence, the convergence of multiple independent lines of inquiry that builds confidence in a conclusion. The void hypothesis will stand or fall based on this accumulated evidence. If all the different techniques point to the same answer, it will be accepted. If they give conflicting results, it will be revised or discarded. Science is self-correcting, but the corrections can take time, decades sometimes. The Hubble tension has been a recognized problem for about a decade now, and we're still working through the possible explanations. The void hypothesis is only a few years old as a serious contender. It will probably take another decade of observations and analysis before consensus forms around either accepting it, rejecting it, or modifying it into something more nuanced. During that time, astronomers will continue observing, theorists will continue calculating, and gradually, the picture will sharpen. This is the reality of scientific progress. It's patient, methodical, careful. Not the sudden breakthroughs that popular culture celebrates, but the steady accumulation of knowledge, one observation at a time, one paper at a time, one conference at a time. It's less dramatic than the myths suggest, but no less profound. We're learning truths about the universe that will remain true long after we're gone. We're building knowledge that future generations will inherit and build upon. And in the meantime, we live our lives here in the void, whether we know it or not, whether it affects us or not. The void is our home on the largest scales, the cosmic structure we're embedded in. It's as much a part of our address as our planet, our star system, our galaxy. Earth, solar system, Orion Arm, Milky Way, local group, Virgo supercluster, Laniakea supercluster complex, and now the local void, 2 billion light years across, mostly empty, with us somewhere inside. That's a lot of address. Each level represents a different scale, a different frame of reference. On the scale of a human life, Earth is everything. On the scale of spaceflight, the solar system is the relevant frame. On the scale of interstellar travel, the galaxy matters. On the scale of cosmology, the void matters. Each scale has its own dynamics, its own relevant physics, its own characteristic timescales. What happens on one scale might barely affect what happens on another. The void grows over billions of years, but that growth doesn't affect the orbit of the Earth around the Sun. The Sun orbits the Milky Way over 200 million years, but that motion doesn't affect the expansion of the void. These processes are decoupled, operating independently on different scales. Yet they're all part of the same universe, all governed by the same fundamental laws. Gravity works the same way whether you're studying planetary orbits or cosmic voids. It's just applied to different mass distributions over different distances. This multi-scale nature of the universe is one of the things that makes it so rich and fascinating. There's no single correct level of description. Every scale reveals different phenomena, different structures, different stories. You can spend a lifetime studying just one scale and never exhaust its complexities. Planetary science, stellar astrophysics, galactic dynamics, cosmology, each is a vast field with thousands of researchers working on countless unsolved problems. And yet, there are connections between scales. Stars form from gas clouds that were enriched by previous generations of stars. Galaxies grow through mergers and gas accretion. The cosmic web formed from quantum fluctuations in the early universe. Everything is connected through chains of causation, stretching across time and space. The void we live in exists because of fluctuations that occurred 13 billion years ago. Those fluctuations occurred because of quantum mechanics operating during inflation. Inflation occurred because of physics in the first fraction of a second after the Big Bang. And the Big Bang itself? Well, we don't know what caused that. It's the ultimate question, the beginning of causation, the first link in the chain. Maybe there's an answer. Maybe there's a quantum theory of gravity that explains how universes begin. Maybe our universe is part of an eternal multiverse where Big Bangs are constantly happening, each one creating a new bubble universe with its own laws and constants. Maybe time itself began at the Big Bang, and asking what came before is a meaningless question because there was no before. These are deep waters, the edge of what physics can currently address. We have ideas, speculations, mathematical models, but no definitive answers. And perhaps that's appropriate. Perhaps the universe should have mysteries, questions that remain unanswered, frontiers that recede as we approach them. If we understood everything, if every question had a settled answer, what would be left to discover? The joy of science is partly in the not knowing, in the exploration, in the gradual illumination of darkness. Each answer we find is satisfying, but it also opens new questions, deeper mysteries. The universe is generous with its secrets, revealing them slowly, keeping us engaged, keeping us curious. Your breathing is slower now, deeper, more regular. Your body has found its comfortable position, that place of rest, where muscles relax and tension drains away. Your mind is drifting, following these thoughts through the void, through the cosmic web, through space-time itself. It's okay to lose the thread, to let words wash over you like waves, carrying you toward sleep. The details don't matter anymore, just the rhythm, the voice, the gentle exploration of ideas too vast to fully grasp. We're floating in a void 2 billion light years across. That's the story we've been telling. But really, we're floating in a bedroom, or wherever you are right now, on a planet that's floating around a star, that's floating through a galaxy that's floating in the void. Scales nested within scales, wheels within wheels, each one turning at its own pace. And you're at the center of all of it, not because you're special in the cosmic sense, but because you're the observer. Everything you experience is relative to you, your position, your motion, your frame of reference. From your perspective, you're stationary, and the universe moves around you. The sun rises and sets because Earth rotates. But from your subjective experience, the sun moves, and you stay still. The stars wheel overhead because Earth orbits the sun and rotates on its axis. But from your experience, you're standing still, and the cosmos revolves around you. In a sense, you are at the center. Not the physical center, but the experiential center, the point of view from which everything else is measured. This is the old geocentric intuition, the feeling that Earth is stationary and everything moves around it. Science taught us that this is an illusion, that Earth is just one planet among many, orbiting an ordinary star in an ordinary galaxy. But science also taught us that motion is relative, that there's no absolute reference frame. So in a way, the geocentric intuition isn't entirely wrong, it's just limited. From your frame of reference, you are stationary. But from another frame of reference, you're moving at hundreds of kilometers per second through space. Both perspectives are valid. Neither is more true than the other. This relativity of motion extends to everything. The void is expanding away from us, or we're floating through it, or both, depending on how you choose to describe it. The cosmic microwave background appears to be moving relative to us at 600 kilometers per second, or we're moving relative to it, or both. Motion only makes sense as a relationship between objects. There's no absolute motion, only relative motion. Einstein understood this deeply. His theory of special relativity showed that time and space are relative, that different observers moving at different speeds will measure different durations and different distances, and both measurements will be correct. His theory of general relativity extended this to gravity, showing that mass and energy curve spacetime, and that curved spacetime tells objects how to move. There's no absolute space, no absolute time, only the relationships between events and observers. This relational nature of reality is profound. Nothing exists in isolation. Everything is defined by its relationships to everything else. A galaxy's motion is defined relative to other galaxies. A void's density is defined relative to the cosmic average. Even basic properties, like position and velocity, are relational, meaningful only when compared to something else. The universe is a web of relationships, not a collection of isolated objects. And consciousness is part of that web. Your awareness right now, this experience of listening and thinking and gradually drifting toward sleep, is a relationship between your brain and the sensory input it's receiving, the memories it's accessing, the internal states it's processing. Consciousness isn't a thing that exists independently. It's a process, an ongoing relationship between neurons and signals and feedback loops, all happening in the physical substrate of your brain. When you sleep, that process changes. The relationships shift. Some neural connections strengthen, others weaken. Memories are consolidated. Irrelevant information is pruned away. The brain reorganizes itself, preparing for the next day. Sleep isn't just rest. It's active processing, essential maintenance, a different mode of consciousness rather than the absence of consciousness. And dreams, those strange experiences that occur during sleep, are your brain's way of exploring possible patterns, making sense of the day's experiences, running simulations of scenarios that might be useful in the future. Dreams feel surreal because they're not constrained by external sensory input. Your brain is free to combine memories and ideas in novel ways, creating narratives that don't have to obey the rules of waking reality. You might fly, or breathe underwater, or talk to people who are no longer alive. In dreams, anything is possible because the simulator has no obligation to match external reality. In a way, dreams are your personal multiverse. Each dream is a different universe with different rules, and you experience them all, night after night, exploring possibility space from the comfort of your bed. The multiverse hypothesis in cosmology suggests that other universes exist with different physical laws. Your dreams show that other realities exist inside your own mind, equally real to you while you're experiencing them, even though they're generated internally rather than externally. The boundary between internal and external reality is more fluid than we usually assume. What you experience is always a construction, a model built by your brain from sensory data. The real world you experience is a simulation running in your neurons, hopefully matching external reality, but always mediated by your perceptual and cognitive systems. In that sense, dreams aren't fundamentally different from waking experience. Both are simulations. Dreams just happen to be simulations that don't match external reality, while waking experiences usually do. This might sound unsettling, the idea that you never experience reality directly, only your brain's model of it. But it's also liberating. It means your experience of the world is flexible, shaped by your expectations, your attention, your mood. You can learn to perceive things differently by training your perceptual systems. You can change your experience of reality by changing the model your brain constructs. Meditation practices work on this principle, teaching you to notice aspects of experience you normally overlook, to shift your relationship with thoughts and sensations. And sleep is the ultimate shift in experience. The transition from waking consciousness to sleep is a gradual change in brain state, from one mode of processing to another. As you drift off, different parts of the brain become more or less active. The prefrontal cortex, responsible for planning and decision-making, quiets down. The default mode network, involved in self-referential thinking and mind-wandering, changes its activity patterns. The brainstem and thalamus shift from promoting wakefulness to promoting sleep. It's a carefully orchestrated transition, different neural systems cooperating to change the overall state, and you can feel it happening if you pay attention. The thoughts become less logical, more dreamlike. Images and memories drift through awareness without clear connections. The sense of time distorts. Minutes can feel like hours or seconds, The boundary between self and world blurs. You might not be sure if you're still awake or already dreaming. This liminal space between waking and sleep is fascinating, a window into the mechanics of consciousness itself. Some meditation traditions focus on maintaining awareness through this transition, staying conscious as the body falls asleep. Lucid dreaming practices aim to bring waking awareness into the dream state. These practices suggest that consciousness is more flexible than we usually experience, that the boundaries between states are permeable, that with training, you can navigate these transitions deliberately, rather than just letting them happen automatically. But for tonight, for now, there's no need to control anything. Just let the transition happen naturally. Let your body sink into rest. Let your mind wander where it will. The void, the cosmic web, the universe's structure, all of these ideas can fade into the background. They'll still be there tomorrow, still waiting to be explored further. The universe isn't going anywhere. It will continue expanding, evolving, revealing its secrets slowly over the coming years and decades. And you'll be part of that process if you choose to be. Maybe you'll read about new discoveries, new observations that clarify the void hypothesis. Maybe you'll see headlines announcing that we've confirmed our position in a cosmic underdensity, or that we've ruled it out and found a different explanation for the Hubble tension. Maybe future astronomers will refine the measurements, shrink the error bars, narrow down the possibilities until only one answer remains. Or maybe the mystery will deepen. Maybe new data will reveal complications we haven't anticipated. Maybe the universe will surprise us again with its complexity. That's happened before. Every time we think we've figured something out, we discover another layer of subtlety. The universe seems designed to keep us humble, to remind us that our understanding is always provisional, always subject to revision as new evidence emerges. But that's the beauty of it. The universe doesn't owe us comprehensibility. The fact that we can understand anything at all is remarkable. Conscious beings emerge from the interplay of physics and chemistry, complex enough to study the cosmos that created them, to ask questions about voids and expansion rates and the structure of space-time. That's extraordinary. That's the real wonder, not just the universe itself, but the fact that the universe has parts that can study other parts, that awareness and curiosity and the drive to understand have somehow emerged from the quantum foam.